Hot embossing is a method that could be useful for micromachining soft materials such as polymers. It has promising applications in the development of biomedical, microelectromechanical systems for microfluidic devices and drug delivery. It has also been a successful technique for many optical technologies, such as micro-optical lenses, diffraction grating, and optical waveguides. As seen in the figures, these structures are usually on the micron scale, which is the scale where hot embossing is more promising. A typical way in which hot embossing could be used in micromachining is as follows. First, you spin coat a polymer film onto a substrate. You could then press a mold into the polymer through hot embossing, leaving a polymer replicating the mold just as a stamp. The process will leave a residual layer that could then be etched away to create the opening desired. Let us now focus on the hot embossing procedure itself. The system consists of three main components: the mold or tool that carries the microscale features we wish to replicate, the substrate, which is a flat surface to which the polymer is typically attached, and the polymer film, which is what we are going to be transcribing. The system is heated to above the glass transition temperature so that the polymer will become soft. A vacuum is also applied in some cases, especially when we have a high aspect ratio that we want to replicate, and this is to prevent air bubbles from reducing the quality of the replication. Once the system has reached the appropriate vacuum and temperature, the embossing tool is slowly pressed into the mask. This is typically done at a rate on the order of 1 millimeter per minute. The embossing process is usually force controlled. We push the mask and polymer together to some preset maximum force that we determined before we started the process. The system is then held at this constant force and temperature so that the polymer can flow through the cavities and flow into the mask to replicate the structure of the mask accurately. The system is then cooled to below the glass transition temperature in order to solidify the created imprint. The process of de-embossing or demolding is actually considered to be the most difficult aspect of hot embossing. In order to remove the mold from the polymer, we need good adhesion between the polymer and the flat substrate. Due to the frictional forces between the mold and the polymer, de-embossing must be done very carefully to avoid damage or distortion of the created structure. The process depends on a few key parameters: the packing force, which affects the pressure experienced by the polymer and is what drives the polymer to fill the cavities in the mask. The temperature affects the properties of the polymer film itself, such as its viscosity. The holding time is defined as the amount of time that the embossing process is conducted at a constant force and temperature. The holding time determines how well the polymer fills the cavity. These factors combine to affect the residual stresses in the film after the process and the quality of the replication. The dependence of the process on these parameters depends on the geometry of the mold itself, quite strongly. The process is best modeled with some sort of finite element software to determine the effects of the process parameters for a given geometry. To develop a simple process model, let's consider a simple geometry, one where the mold contains periodically arranged cavities. We can assume that the polymer undergoes ideal viscous flow, which will allow us to model our system using classical fluid mechanics. First, let's apply laminar flow as our framework. Laminar flow gives us a relationship between velocity, denoted as u, the pressure gradient, and the viscosity, denoted as eta. Our pressure gradient, in this case, is the applied pressure, adjusted for the contact area between the polymer and the stamp. We can use this description of the velocity to then estimate the time it would take to fill the cavity, which is what we referred to as the holding time on the previous slide. The holding time decreases with increased pressure and with decreased viscosity, as we would expect. In addition, we see that a wider width actually decreases the time to fill the cavity. Instead of assuming laminar flow, we can also develop a process model by using squeeze flow theory, where the rate at which the cavity is filled is related to the change in the height of the polymer, denoted as h of t in the schematic on the top right. The resulting equation for time using this methodology was presented by Heiderman et al. And is shown below, where hf and h naught are the initial and final thicknesses of the polymer film. The results of this methodology show similar relationships to the previous one, with the holding time decreasing with increased pressure and decreased viscosity. The formulation using squeeze flow reveals another interesting dependency, namely that a thicker initial polymer film will lead to shorter holding times, which can be shown more rigorously by plugging in an equation for HF. Two formulations actually describe different underlying physics. The laminar flow model assumes that the flow occurs essentially as a circular mound growing in the middle of the cavity, whereas the squeeze flow theory describes a process that involves the polymer interaction with the surface of the mold. The laminar flow model actually assumes a no-slip condition with the walls, and therefore neglects this interaction with the walls. The temperature can be added to this picture by considering the temperature dependence of viscosity. This is typically treated using the Williams-Landau-Ferry model, or WLF model. In this model, we determine the viscosity as a function of temperature for temperatures above the glass transition temperature. T naught is essentially the glass transition temperature plus some constant temperature. Using the equations developed, the approximate dependencies of the time required to get a high-quality replication of the mold on geometry, pressure, temperature, and polymer material can be delineated.